We hear the words mass and weight thrown around like they're the same thing all the time, but in the world of physics, they are totally different. So let's dive in and finally get to the bottom of this. Okay, just think about this for a second. If you were on the moon, you'd weigh about a sixth of what you do here on Earth. I mean, you could jump way higher, you'd feel incredibly light. But would the amount of actual stuff that makes you, well, you, have changed at all? No way, right? That simple idea is the key to understanding everything else we're about to cover. So let's kick things off with the part of you that doesn't change no matter where you are in the universe. Let's talk about mass. And really, it's that straightforward. Mass is just the measure of how much matter, how much stuff is packed into an object. Your mass, the mass of the chair you're sitting in, the mass of an entire planet, it's a fundamental property. It's constant. It just doesn't change. Now, in science, the standard unit we use for mass is the kilogram, or kg. You'll also see it measured in grams, especially for smaller things, and the conversion is super easy to remember. 1 kilogram is just 1,000 grams. Okay, and this is where the idea of mass gets really, really cool. It's not just about the amount of stuff, it's also a measure of an object's, well, you could call it laziness. Physicists call it inertia. It's an object's natural resistance to any change in what it's doing. This is the perfect way to picture it. Imagine trying to push a car versus pushing a bicycle. The car has way more mass, which means it has way more inertia. It is much, much harder to get that car moving. And once it is moving, it's a lot harder to stop. The bicycle, it has less mass, so it's a piece of cake to start and stop. That difference you feel? That's inertia, right there in action. All right, so we've got mass, this constant amount of stuff. But here's the thing. Mass is almost always being pulled on by this invisible force. And that, of course, brings us to gravity. So any object that has mass, and I mean any object, creates a gravitational field around it. You can think of it like a zone of influence. When another object with mass comes into this field, it feels a pull, a force of attraction. We're living inside a massive gravitational field right now, the one created by our planet. It is constantly pulling on you, on me, on everything with mass, tugging it all toward the center of the Earth. It's the whole reason why when you drop something, it falls down, not up or sideways. Okay, so we have mass, the stuff you're made of, and we have gravity, the invisible force pulling on all that stuff. So what happens when you put them together? Well, that's when you get weight. And there it is. That's the big difference. Weight isn't the matter itself. It's the force that gravity exerts on that matter. Your mass is always the same, but the force of gravity can change depending on where you are in the universe. And that's exactly why your weight is different on the moon than it is here on Earth. And like with so many things in physics, it all comes down to a beautifully simple equation. W equals m times g. Weight equals mass times the gravitational field strength. This is the formula that links the two ideas together perfectly. It shows you right there that your weight depends on two things: your mass and how strong gravity is. So let's just break down the key details here. Since weight is a force, we measure it in newtons, not kilograms. And that force always pulls straight down toward the planet's center. Here on Earth, the strength of gravity, that G in the formula, is about 10 newtons for every single kilogram of mass. Now, since mass and weight are totally different properties, it makes sense that we need different tools to measure them. So how do we actually do it? To figure out an object's mass, you'd use something like a beam balance. What it's actually doing is comparing an unknown mass on one side to a set of known masses on the other. Because gravity is pulling down equally on both sides, it kind of cancels itself out, leaving you with a true measure of just the mass. But to find weight, you need a spring balance or a force meter. That tool directly measures the downward pull, the actual force of gravity on the object. Okay, we've covered a ton of ground. Let's bring it all together for one final side-by-side comparison to make sure these ideas are totally locked in. Let's just run through this real quick. Mass, what is it? It's the amount of matter. Its unit, the kilogram. Its key property, it is constant everywhere, and we measure it with a beam balance. Now let's look at weight. What is it? It's the force of gravity acting on that mass. Its unit is the newton. Its property, it changes depending on gravity, and we measure it with a force meter or a spring balance. See? Simple, clear, and fundamentally different. And that brings us to one last thought.
An astronaut floating around in deep space is often called weightless. And they pretty much are, because the pull of gravity is so weak out there. But based on everything we just covered, you know the answer to that second question, right? Are they massless? Absolutely not. All the stuff they're made of is still there, full of inertia. If you tried to push them, you'd still feel that resistance. They have mass, they just don't have weight. And now you know exactly why.